Thank you for watching, and welcome to the next video in my series on basic statistics. Now, since this is part 2 of a 2-part video, I'll keep this intro short. But just keep in mind, if you're watching this because you're struggling in a class, stay positive and keep your head up. You're smart and talented, and you must have the confidence that you can work through it. Please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way when I upload a video, you know about it. If you like the video, please give it a thumbs up, share it with classmates or colleagues, or put it on a playlist. That does encourage me to keep making them for you. And just keep in mind that these videos are meant for individuals who are relatively new to stats. So I'm just going over basic concepts. So all that being said, let's go ahead and get started on part 2. So remember, in part 1 of this video, we talked about the conceptual background of the single sample t-test. And we did that through the lens of the single sample z-test, which we learned about in previous videos. So remember, the main difference is that in the z-test, we know sigma, or sigma is given to us. And of course, that's the population standard deviation. In the t-test, we are not given sigma, or we do not know it. Therefore, we estimate it using the sample standard deviation. So that's the primary difference between the two. Now, from part 1, we walked away with 2 conceptual pillars. The first one is that the alpha level affects the location of our critical values. So if we have an alpha of, say, 0.10, that's going to be a probability of 0.9 in the middle of the distribution. Now, if we go to an alpha of 0.05, that's going to be 95% probability in the middle. So more. Well, because we have more probability in the middle, what has to happen to our critical values as far as their location? Well, they have to move outward. Now, let's say we go from an alpha of 0.05 to an alpha of 0.01. So the probability is now 0.99 in the middle of the distribution. Then what has to happen to the location of our critical values? Well, they're going to have to go out even further to accommodate that 99% area or 0.99 probability. So the alpha level affects the location of our critical values in our distribution. That's the first important point. The second important point is the difference between the z-distribution and the t-distributions. Because remember, every sample size has its own t-distribution. But in general, we talked about the following idea. For any given z-distribution, if we take the t-distribution of, say, a moderate sample size like 20 or 25, if we look at the critical values of that z-distribution as compared to the t-distribution for a given alpha, what happens to the location of the critical values in the t-distribution? Well, again, they move outward towards the tails ever so slightly. And why is that? Well, remember the t-distribution has a little bit less probability in the middle, a little bit more in the tails. So if we compare it to the z-distribution, the critical values are going to be slightly outward to accommodate that sort of squishiness of the t-distribution. So these two things affect the location of the critical value. The alpha level and the t-distribution as far as its sample size goes. Because in general, as the sample size gets smaller, the critical values are going to be pushed outward because there is more uncertainty in the sampling distribution. Now, why am I telling you all this? I spent 3 minutes telling you this. Why? Well, the whole idea of hypothesis testing is about the location of the critical values. So if our test statistic is on one side of the critical value or the other, that completely changes what our conclusion is. So you have to understand what's happening with the location of the critical values in terms of the alpha level and the characteristics of the t-distribution. Because as we'll see coming up here in a few minutes, it can really change the outcome of your problem. So let's go ahead and take a look at our first example. So this is the same problem I used in the z-test video, but I changed it to adapt it for the t-test. So we're not going to reinvent the wheel, we'll just change a few things and use the same problems. So let's say a report from 6 years ago indicated that the average gross salary for a business analyst was $69,873. Now, since this survey is now outdated, the BLS wishes to test this figure against current salaries to see if the current salaries are statistically different from the old ones. So we're testing to see if the current population of salaries is equivalent to the old population of salaries. Now, based on this sample, we found a sample standard deviation of 14,985. Now, again, we do not know sigma. Therefore, we'll have to estimate it using this sample standard deviation. Now, for this study, the BLS will take a sample of 12 current salaries. So, look at what we have here. We have a hypothesized population mean, that's 69,873. We have a sample standard deviation, 14,985. And we have N, our sample size. We almost have everything we need to conduct our test. But of course, we're not going to do that yet. We're going to set up a proper hypothesis. So, our null hypothesis is that the current population of salaries is equivalent to the old population of salaries. Therefore, the alternative is that the current population of salaries is not equivalent to the old population of salaries. Now, this would be a two-tailed test. The salaries could be higher or they could be lower. I mean, we're in a recession right now, so they could be lower. Now, since sigma is unknown and n is small, we'll use the t distribution. And there's the t-statistic formula over there on the right. It looks very similar to the z-statistic formula. So specify the type 1 error rate. Now, this is my choice. I'm going to choose an alpha of 0.05. I could have selected an alpha of 0.01 or 0.10, but I choose the middle ground, and I'll select an alpha of 0.05. That means I accept the possibility that I might make a type 1 error 5% of the time. So state the decision rule. Now remember, we are using the t-distribution, so the location of our critical values in our regions will depend on our sample size and our alpha. So in this case, our sample size is 12. Therefore, our degrees of freedom is 11. So we will consult our t-table. We'll find the column that is a two-tailed test at an alpha of 0.05. Then we'll find the row that is 11 degrees of freedom. We'll find where those intersect, and we find that we have a t-value of 2.201. So our critical values are t plus or minus 2.201. Then we'll gather our data. So we have 12 in our sample, and we found out that our sample mean is 79,180. So now we have everything we need to go ahead and figure out our test statistic. So we have our sample mean of 79,180, our hypothesized population mean of 69,873. There's almost a $10,000 difference there. Our sample standard deviation of 14,985, our sample size of 12. So we can go ahead and substitute all that into our formula. So we have 79,180 minus 69,873 divided by 14,985 divided by the square root of 12. So we just substituted everything in there. And that generates a t-statistic of 2.15. So that is our test statistic. Now we'll go ahead and put that in the context of our sampling distribution. So our hypothesis there are the same. We have our hypothesized mean there in the middle, our non-rejection region in blue, and our rejection region in the brown. So where does our test statistic fall? Well, it's 2.15, so it falls right there. Now what do we notice? Since the test statistic is in the non-rejection region and not beyond the critical t-value, we failed to reject the null hypothesis. So it's not out of the ordinary that this sample came from a population with a population mean of 69,873 as we hypothesized. Now, it's in the upper area of our non-rejection region, but that really doesn't make a difference. It's either in that region or it's not. So we just happened to get a sample that fell here. Now, we could have gotten a sample that fell in the same place on the other side. So maybe minus 2.15. Or we could have gotten a sample that fell right in the middle. Or we could have gotten a sample that fell in the rejection region. That's the idea of a sampling distribution. We expect 95% of our samples to be in this blue region, and ours just happened to be one of those. Now, had it been a bit higher, it would have been outside, but that is just the idea of chance. Our sample happened to fall right there. So we failed to reject the null hypothesis. And remember, our t-value was 2.201, so it would have had to have been beyond 2.201 for us to actually reject the null hypothesis. Now let's do the same problem, but change the sample size. So we're going to go from a sample size of 12 to a sample size of 15. Let's see what happens. So everything else is the same. Sample means the same, hypothesized means the same, deviation is the same, just the sample size has changed. So we'll go ahead and substitute all that into this formula. Now we have a t-statistic of 2.41. So that is our test statistic. Let's go ahead and place it on the curve. So here everything is the same. So our degrees of freedom are now 14, because remember our sample size was 15, so our degrees of freedom is 14. Now if we go to our t-table, we find that the critical t-value is plus or minus 2.145. So that is the critical value there on the bottom. Now remember that for degrees of freedom of 11, it was plus or minus 2.201. So when we increased the sample size, what happened to the location of the critical t-values? Well, they moved inward, ever so slightly, but they did move inward. And why is that? Well, we'll talk about that here in a second, actually. So our t value is 2.41. So look where it falls. Well, it's now in the rejection region. So if you look over there on the left, if t is greater than 2.145, we reject the null hypothesis. So all we did here was change the sample size from 12 to 15. And now we came up with a completely different conclusion. And the question is, why is that? Well, the larger sample size decreased the standard error of the mean. So the larger sample size decreased the standard deviation of this distribution. It made it narrower. So what ended up happening is it made our sample stand further out on its own. It made it a little bit more likely to belong to a different population that does not overlap much with this population. It created a separation between our sample, x bar, and our hypothesized sample mean. So the larger sample size decreased the standard deviation, the standard error of the mean, of this distribution. So it kind of like sucked in its middle. It's kind of like when your pants don't fit, so you suck in your belly. That's kind of what happened to this distribution. When we increased the sample size, it pulled it inward towards the middle, and that left our poor t-statistic standing out there by itself. Now also, the larger sample size led to a higher degrees of freedom. This brought more probability as well in towards the middle of the t-distribution around our hypothesized population mean. So being inside the non-rejection region, this blue area, is a bit more exclusive club. So you can think of our sample mean as kind of like someone outside the bar who cannot afford to get in to hang out with the cool people. So two things went on here, and that's why we went over all that conceptual information. The larger sample size decreased the standard error of this distribution, so it kind of sucked in towards the middle. Also, the larger sample size led to a higher degrees of freedom. So that brought more probability in towards the middle as well. So two things going on there. And therefore, our sample mean is the same sample mean, but this time it was left outside of the non-rejection region. And all we did there was change the sample size from 12 to 15. Okay, so example 2, Starbucks customer satisfaction. So Starbucks is interested in assessing customer satisfaction in the Canadian city of Toronto, Ontario. To conduct the study, Starbucks asked 25 customers in the city the following question. Compared to other coffee houses in Toronto, would you say the customer service at Starbucks is much better than average, that's a score of 5, better than average, that's a score of 4, average, a score of 3, worse than average, a score of 2, or much worse than average, a score of 1. And of course, we call that a Likert scale in research. Now, we found that the mean rating was determined to be 3.5. Also, based on this sample, the standard deviation was found to be 1.4. So our sample mean was 3.5, our sample standard deviation was 1.4. So let's set up our hypotheses. So our null hypothesis is that the mean customer sentiment or feeling is 3 or less. So average or lower. Therefore, the alternative hypothesis is that customer sentiment is higher than average or greater than 3. Now this will be a one-tailed test, and we can tell that by the signs in our hypothesis. And Starbucks, remember, is interested in a better than average rating. So here's what they're kind of trying to do in this test. They're setting up a null hypothesis that says, oh, our customer sentiment is average or lower. And then we're going to collect some data. And we're going to see whether or not our data support the idea that we can reject that null hypothesis. If we can reject that null hypothesis, then we can proceed to the alternative that says customer sentiment is better than average. Now, since sigma is unknown and our sample size is small, we will use the t distribution. So the t formula is over there on the right. So we'll go ahead and specify the type 1 error rate. Now, I'm going to choose an alpha of 0.01, and that's just my choice for this one-tailed test. Then we'll state our decision rule. Remember, our sample size is 25. Therefore, our degrees of freedom is 24. So we need to go to our t-table, find the column for a one-tailed with an alpha of 0.01, find the row for 24 degrees of freedom, and when we do that, we come up with a critical t-value of 2.492. So if our test statistic is greater than 2.492, we will reject our null hypothesis. Now on the curve, we can actually place it. So remember, with an alpha of 0.01, what we're saying is that we have a 1% chance, or we're willing to accept a 1% probability of committing a type 1 error. So that's the 1% in the upper tail. And therefore, 99% of our sample means should be in the blue. So we'll place our critical value, our t-value, right there. So 2.492. Of course, then we'll gather our data. So we had a sample size of 25, and our mean was 3.5. Now we can calculate our test statistic. So our mean of 3.5, our hypothesized mean of 3, sample standard deviation of 1.4, and sample size of 25. So we'll go ahead and substitute those numbers into our formula, and we arrive at a t-statistic, our test statistic, of 1.79. So now we have to place that in the context of our sampling distribution. So the same hypothesis, we have our mean was 3.5. Our critical value was 2.492. Our test statistic was 1.79. So what happens? Since the test statistic is inside the non-rejection region and inside the critical value, sort of inside of towards the mean, we fail to reject the null hypothesis that customer satisfaction is at or below average. Okay, so we fail to reject the null hypothesis. It is higher, so it's 3.5. It is higher, but the sample is just one of many that could be inside this non-rejection region. The sample mean would have had to have been much higher to actually surpass that critical value. Now the question is, what would that sample mean have to be to surpass that critical value of 2.492? So finding the hypothetical sample mean that aligns with our t critical value of 2.492 is actually fairly straightforward. Remember when we first found our t-statistic, the t was the unknown, and our sample mean was what we found in our data analysis. So now we're going to flip that a little bit on its head. Now we know the t value, and we want to know the sample mean that corresponds with that critical t value. So our x bar is now the unknown, and our t is known. So again, we'll just use our handy algebra from many years ago to solve for x bar. So we'll go ahead and simplify our denominator. So that's 0.28. We'll multiply both sides by 0.28. So we have 0.698 equals x bar minus 3. So we'll go ahead and simplify that. And we have a sample mean of 3.698. So therefore, any sample of size 25 with a mean that's greater than 3.698 would lead to the rejection of the null hypothesis, assuming the same sample deviation, which is not all that likely, but we'll assume, and the same alpha level. So the sample mean of 3.698 is the sample mean that would hypothetically fall right onto our t critical value. Now if we go ahead and look at our distribution again, we can actually sort of write these in. So where t equals 1.79, that's the test statistic from our analysis, our sample mean was of course 3.5. Now the sample mean that would correspond with our critical value of 2.492 is 3.698. So you can see the difference between our sample mean and the mean that would have been required to reject the null hypothesis. So based on our alpha of 0.01, we know that 1% of our area is in the upper tail. So that's the 1% past our t critical of 2.492. Right there. Now in the p-value method, we ask how much area or probability is above our test statistic. So we're interested in how much area is to the right of our test statistic. Now using a t-table, we can tell that the probability is between 0.05 and 0.025. So we kind of eyeball it between two knowns. Now in Excel, we can find it exactly. Excel gives us a p-value of 0.043. Now that's greater than 0.01. So we know that we cannot reject the null hypothesis. Now this is often referred to as the observed significance level. So again, we can find the p-value here to actually show that we cannot reject the null, because the area to the right of our t-statistic is 0.043, but our alpha is 0.01. So therefore, if we wanted to reject the null, it would have to be less than 0.01. Now, how did I find that in Excel? So remember, our degrees of freedom are 24, our t-value is 1.79. So we just use this formula in Excel 2010. It's t.dist.rt. That stands for right tail. It saves us from having to subtract from 1. So 1.79 is our t-value, and 24 is our degrees of freedom. So you can actually use the function tool in Excel. It's a little f of x button you can press, and it'll tell you exactly what to put in. So our t-value is 1.79. Our degrees of freedom were 24. So if we look where it actually solves it, the formula result is 0.043. And that's how I came up with the p-value of 0.043 in the previous slide. Okay, so that wraps up our two examples on single sample t-tests and the t-distribution. So just a reminder of the process so you can do it correctly. Always start with a well-developed, clear research problem or question. No fancy stats will solve a bad research problem. So always hone in, always clarify your problem before you start. Establish your hypothesis, both null and alternative. Determine the appropriate statistical test and sampling distribution. And again, this depends on really two things. Do you know sigma or do you not know sigma? Is your sample size below 100 or not? So again, that will determine whether or not you're using the z-distribution and z-test or the t-distribution and t-test. Choose your type 1 error rate. Again, that's up to you. Then state your decision rule. So based on the statistical test and distribution you're using and your error rate, you will come up with a decision rule that says if my t-value falls here, I cannot reject the null hypothesis. If it falls here, I have to reject the null hypothesis. Then gather your sample data. Once you have your sample data, calculate the test statistic. Once you have the test statistic, you compare that to your decision rule and then state your conclusion. Once you have the conclusion, you can then make some sort of real-world recommendation or some real-world publication, whatever your application may happen to be. Okay, so that wraps up part 2 of our video on the single sample t-test. And I really hope you have a firm grasp of how all this comes together. So we talked about the t-test as compared with the z-test. We talked about what happens when you maybe even change one small parameter like the sample size. In that case, we got a completely different conclusion by changing the sample size by 3. So you can see that some of these tests are very sensitive to their parameters. And I really want you to understand how these things affect the overall test, the alpha level, the sample size, and things like that. So just keep in mind if you're watching the video because you're struggling in a class, stay positive and keep your head up. If you're watching this, it means you've accomplished quite a bit. You're smart and talented, and you can get through it. Please feel free to follow me here on YouTube, on Twitter, on Google+, or on LinkedIn. That way when I upload a new video, you know about it. And it's always nice to hear from people who watch my videos online. Life is much too short, the world is much too large for us not to take the opportunity to connect with one another. If you like the video, please give it a thumbs up, share it with classmates or colleagues, or put it on a playlist. And finally, just keep in mind the fact that you're on here trying to learn, trying to improve yourself as a student or as a business person or whatever else you may be doing, that's what really matters. I firmly believe if you have the right learning process in place, the results will take care of themselves. So, thank you very much for watching, and look forward to seeing you again next time.